Thanks very much for the very kind introduction. It's a real pleasure and honor to be here with you today. This is my first time to the a forensic conference of this kind, and I've been very impressed with all of the speakers and the posters so far. Been very impressive to me. The couple of things that I've learned is the importance in this field for continuing education seems to be critical. The need for new research into new processes for analysis, and also a way to identify resources of how you can get information and more information. And so what I want to do over the next 30 minutes is really tell you a little bit about some resources that are available to you in the College of Textiles at NC State and offer those to you. And also to give you an overview of some of the manufacturing facilities and processes and capabilities in the textile industry and where some of the things are going. I noticed from a couple of the posters, several of the posters yesterday, one was on technical textiles, which was very good, and some new analytical techniques of fibers and dyed fibers, Raman spectroscopy and capillary electrophoresis mass spec as well. So there is some interest in this area, obviously, and a real need for it. So just as an overview, if you don't mind, indulge me in letting me tell you a little bit about the College of Textiles at NC State and some of the breadth that we have as a resource to you. And then I'll give an overview of some of the innovations in textile manufacturing, some technical trends that we're seeing, both what's happening right now and what you should anticipate in the next few years. And that might impact some of the analytical needs that you have. And also to overview a very fast-growing area in textiles, which is non-woven technology, and that incorporates bicomponent fibers. So the college is College of Textiles at NC State is the largest in the West. We have 50 faculty members, about 800 undergraduates currently, and about 150 the PhD or master's students. They do research in a variety of areas, and I'll tell you a few of those in a moment. We have model manufacturing facilities for everything from spinning to chemical finishing. And we have two centers. One is the Nonwovens Institute and the Textile Protection and Comfort Center, both of which could be of significant value in trace evidence potentially. We like to call it from molecules to markets. We were basically focused into several areas: chemistry, engineering and technology of fibers and their manufacture, marketing and merchandising, and also even fashion and brand management. We maintain excellent relationships, and this is where we could be a clearinghouse for trace evidence analysis and some of your needs. All major dyestuff industries and chemical industries, all related to textiles, all major fiber producers, and also the US retailers that we have very close contact with, as you can see some of the key retailers there. Something to point out is that most of the US retailers maintain samples of each of their production batches that are produced from around the world, so globally. And so that is a potential, that is a database that's there. It's not searchable, but there is a possibility to form that into something that is searchable in the future, and that's something that I'm interested in. And if you have an interest in that also, I'd be interested in talking to you. So our research areas break down into chemistry and engineering. There are others as well, but perhaps less relevant to this symposium. Dye chemistry and molecular modeling, and that's one of the areas that I'm very interested in. The design of functional finishes, polymer synthesis, so new polymers for fibers, polymer extrusion. I'll overview some of that a little bit later for the production of synthetic fibers. Analytical chemistry, and then on the engineering side, spinning, weaving, and fabric construction, etc. So at NC State in 2004, there was, in North Carolina State, a new forensic science program was initiated, and the idea was that this would be a clearinghouse for anybody that has needs in the forensic field, from anthropology, and I won't read out the whole list, but we're involved in both the chemistry, fibers, and textiles area, and we provide continuing education as well as a research resource. Some of the things that we have in our college that could be of interest to you: distance education, including things like textile fundamentals. If you want to know about how, in detail, how fibers are formed, how we make them into materials, fabrics, and other materials as well. That could be of significant interest to you. And on the forensic side, we have a forensic textile, specifically analytical chemistry based, and then really mainly aimed at CSI, would be discovery and recovery workshops, week-long workshops as well. And we also have an advanced one that's just running, in fact, next week. As part of the CSI-based discovery and recovery, we have a series of pigs that are sacrificed over a period of days. They may or may not be clothed, and we study the removal of trace evidence at a crime scene and help CSI agents to really get the good data and samples that you really need in the lab. So a couple of areas that are ongoing to us that are related to this symposium perhaps are the degradation of natural and synthetic fibers in various soil environments. There has been some work being done on this over the years, of course, but we're looking at some relatively subtle analytical techniques that will be able to identify perhaps how long something has been in this particular environment. Also, we have significant involvement with the dye stuff industry and have ability to characterize lots of dyes. We have some dyes in a database already, and perhaps that could be something that could be augmented with other existing databases that I know that are under development or ongoing. There are other areas that we are interested in, and I'm also interested in what areas of research in dyes, fibers, that you would like to see undertaken. And so please contact me if you have any interest in some kind of fundamental or applied research that would be of value to you. In terms of degradation of fibers, for example, natural fibers obviously degrade quite significantly, and in soil environments, as you can see here, the pHs can be very significant depending on the fiber. So some fibers degrade rapidly in alkaline environments, some very rapidly in acidic environments. So this is a very general findings, but we want to get into a lot more detail in this regard. And a lot of the data that's been done has really looked at just strength loss rather than chemical analysis of these particular fibers. Obviously, synthetic fibers tend to last a great deal longer. We all know about, I think most of the people in the room know a lot about chemistry, I believe, so I don't need to spend any time on this, but I just did want to give a little run-up to how do we get to textiles in the first place. All textiles are polymer-based, so we have to know something about the polymer chemistry involved. All fibers are polymers, all plastics are polymers, and of course all textiles. What is a fiber? Well, we can break fibers down into two areas. One is continuous filaments. Polyester, nylon, acrylic are often made into continuous filaments, and these are very long fibers, maybe hundreds of feet in length, unbroken, or they're relatively short, what we call staple fibers. These can be natural or synthetic, in fact. So that's one thing to consider. Natural fibers. There are about 200 natural fibers, vegetable or animal origin. Asbestos is a mineral-based fiber. Cotton, obviously, is by far the most important fiber in terms of volume. It's about a $20 billion market today. The next most important is wool, which is a shadow of cotton, obviously, 1.3 million tons. Wool isn't really manufactured and used that much in the United States, but it is in many parts of the world very significant. And then synthetic fibers, of course, there are dozens of different types of synthetic fibers. The synthetic fiber industry is really only about 50 or 60 years old. But it's a key part of our lives, of course. Polyester, there isn't just one polyester. There are many different types of polyester. We can dye polyesters with different types of dye depending on the chemistry that's incorporated into the polymer chains. Polypropylene is something that can't be dyed very easily. It's usually colored through in the extrusion process using pigments, but there is some research ongoing there, which I'll tell you a little bit about later. Polyamides, which are nylon 6,6, nylon 6, Kevlar, Nomex, these are all fall under the main heading of an amide material. And then, of course, you can see acrylic. And I'll tell you a little bit more about spandex because that's an area that's growing quite significantly. And then we can also identify what are really chemically modified natural fibers. So these fall under synthetics, but because we've physically change them significantly. Cellulose diacetate, which goes into suit linings and things of that nature, cigarette filters, and also viscose, which is a regenerated cellulose, one of which is a relatively new fiber, which is growing in volume, is something called lyocell. This is an environmentally benign spinning process that produces a fiber with some interesting properties. It's very silk-like properties, and that's something that can potentially be analyzed by IR. And at Textiles, what do we call textiles at NC State? It's everything up to and including paper. Paper is a fiber-based material, but we don't generally call that a textile because the fiber lengths are relatively short and we can't spin them into yarns. So essentially yarns, woven, fabric knitted, carpet, non-wovens, which I'll tell you a little bit more about, and composite materials such as formica, carbon fiber, set into resins, for example, are other areas that we consider to be textiles. So here's some of the areas of what we're seeing is happening now in terms of technology that could impact you in your analysis. Polyester relatively recently became now the highest volume fiber that's manufactured. It overtook cotton for the first time. However, the average US teenager still owns about 19 denim garments. And so that's a lot of garments, isn't it? And denim is remarkable in its persistence in fashion. But we're seeing a lot more components being folded in and combined with things like denim. Spandex and polyurethane-based fibers in jeans, t-shirts, and other materials as well. And that's something that can potentially be traced back to a manufacturer. Also, we're seeing significant growth in performance sportswear. So these are, for example, polyester or nylon with spandex, other fibers as well, that are manufactured into a weave-type structure that perhaps, for example, wicks away sweat from the body. So it allows you to, when you're undertaking sport and sweating heavily, that you don't feel drenched in sweat as much, like you would with a cotton t-shirt, for example. That's seeing significant use. Potential use of inclusion of microfibers is also of significant interest. That has potential to be able to get definable microscopic analysis of these microfibers that are somewhat unique to a manufacturer potentially. And then also bicomponent fibers, and this is going to be a bit longer to be introduced into the market in a significant way, but it's definitely there today and is likely to grow. Here's a new fiber that you need to be aware of, which is called polylactic acid, or PLA. This was some fiber that was developed through collaboration between Cargill and the Dow Corporation. They now have a new company called, spin-off called Cargill Dow. And it's effectively a regenerable fiber. It's environmentally benign in its production, and it's highly recyclable. Once it's buried in the earth, it will decompose relatively rapidly, but it has the longevity required of a particular fiber in the garment industry, for example, plastics industry as well. So you're going to see this in both plastics and yarn and fibers and fabrics. It's manufactured from, cornstarch, and essentially what is extracted is D or L, the optical forms of lactic acid. And then the key here is the fermentation process in order to obtain this in a very efficient way, which allows the cost to come down for the fiber generation. So polylactic acid itself isn't new, but what is new is the method of process for obtaining what is the monomer to form the polymer of polylactic acid. And so the identification of this monomer present, it could be of interest. You may not be able to see this very easily, but this is the repeat unit for polylactic acid. So again, the market for this currently is minuscule compared to polyester, but this is going to grow. And in the long term, one of the things you should anticipate, and I'm talking about 15 years from now, for example, eventually the cost of polyesters, nylons, and other fibers that are really come from the oil-based industry, the petroleum-based products, they are eventually going to go up in price. And so there will be a significant research effort to be able to replace those plastics and fibers in the future. So I'm not saying 5 years from now, but at some point, if you're new in your career, you are going to see this in 10 plus years or so and become a very significant research effort. So here's some other technology trends that I'm seeing, I would say, that to consider in the near future. Let's take dye chemistry for one. Dye chemistry is really, in terms of textiles, is a very mature industry. The dye stuff manufacturing industries really were based in Germany, Switzerland, the UK, and the United States after the Second World War, before and after the Second World War. But today, over the last 10 years, 10 to 15 years, that's really moved because of environmental concerns into Asia. And the cost of these dyes, a lot of patents have expired, and now there is very little work really going on to develop new dyes for the textile industry. There's lots of interest in high technology applications of dyes, which I'll point to a little bit later. But you shouldn't anticipate anything majorly to change in this area. The replacement of toxic dyes is going to happen, however, so there is some potential there, but I'm not sure how that's going to impact trace evidence with the analytical techniques that you have at your disposal. So here's one example of a research area that looks to be interesting and may impact you. There is a focus on new, what we call functional dyes. So these are dyes that are not produced really for their color from an aesthetic purpose, but they are produced for a particular function. So it might be to use in solar cells, for example. So you don't have to look at a solar panel and it doesn't have to be pretty, but it has to do something very efficiently, which is convert light energy into electrical energy. So porphyrins are a type of dye that do look very promising as applications to what we call self-cleaning textiles. There's an interest in the military in this, and this will also become of interest to the civilians, in my view. There is a new company that's developing fibers, nylon and polyester fibers, that are coated with porphyrins that will essentially be able to act as self-cleaning. And so how do they do that? These porphyrins will absorb light in the long wavelength region of the visible spectrum and in the infrared, and convert that energy. Once the light energy is absorbed, it will be converted to nearby oxygen, and that oxygen becomes what we call singlet oxygen, which is highly reactive, and that will then destroy any microbes that appear to be near the surface of the fiber. Okay, so it's light absorbed by the dye, transferred to oxygen. Oxygen becomes very reactive and then attacks anything that's going to come near it. And it's very short lifetime. And this is a recyclable process. So the dye doesn't get used up. It's continually absorbing and releasing energy. So this has a real interest in antimicrobial applications such as filters and masks. So for bioterrorism type applications, for example, the military is obvious for chemical and biological protection. There is significant research in that area. But also in the civilian side, as I can anticipate, as if, for example, bird flu, there are filters that are now produced that will kill 99.99% of all bird flu on impact with the fiber. So you don't need anything else, and it's regenerable and it has very high durability. So there's possibilities to see and a very large market share projected growth there. Let's look at surface chemistry. There's a couple of areas that I wanted to highlight that could significantly impact trace evidence analysis of fibers, particularly in the IR, for example. And one of them is plasma treatment. Plasma treatment involves high energy plasma gas, it might be argon or other gases, in combination with chemicals that would modify the surface of fibers. So the main integrity of the fiber is unchanged, the strength and everything would be exactly the same, but you will see different functional groups only on the surface. And so you have very targeted activity for high performance fibers. So for example, you may see small amounts of fluorocarbons on the surface that they themselves provide sufficient activity to be able to be both water repellent, soil repellent. Excuse me. Other possibilities are polypropylene, for example. If you treat polypropylene in certain plasma gases, you can start to generate significant levels of carboxylic acids and other functional groups on the surface. So you could get potentially confused with, they think this is polypropylene, but we're seeing evidence of carboxylic acids, and why is that? And so this is something that looks to be cost effective, and it's very low chemical treatment because you're only treating the surface in a very targeted way. So I see this is going to be what I would predict is this is going to be a successful commercial venture in the relatively near future. And then finally, something that we would anticipate seeing a growth in is flame retardant chemistry on application to the fiber surface. So again, plasma may come into play here, but something that we're seeing is that what is likely is a legal requirement for all household items such as drapes, upholstery, to have a significant level of flame retardancy. Carpets. Some do already, but in many cases it's not a requirement. There are requirements, for example, in children's nightwear that everything has to have a flame retardancy and it has to pass a certain level of testing. And so this is going to be a significant area. A lot of the flame retardant applications have environmental concerns, and so there is an area of active interest to be able to get phosphorus-based, for example, non-environmentally high-impact applications in flame retardancy. Here's another area that retailers are becoming more and more interested in. There's lots of knocked-off products coming into the United States. So with logos such as Nike, Reebok, Adidas, that kind of thing, that are not manufactured by those retailers. And so there is a significant interest, and I don't know how quickly this is going to come, but I think in some level it will come relatively soon by some retailers at least. It's what we call security tagging. So some kind of chemical tag that can be applied to a garment that would very rapidly identify it as authentic. So I'm not talking about a label that's stitched into the garment. Obviously, that can be knocked off. But it'll be something that nobody else knows about other than the company, and they can test for imports that are not authentic. So there's a couple of ways that this is being looked at, and so this is still at the research stage, but I think it will be a reality at some point. One possibility is you weave in one particular fiber thread in a garment, or every 100 threads would be one particular fiber that could be very easy to trace. And so that would obviously, in my view, be something of interest to trace evidence. So could you identify what that is and know what the retailers are actually doing? Another possibility is some kind of chemical stamp on the surface, something that's added to the dyeing process that would be, of course, unseen to the average observer, but would have a particular signature. It might have an infrared signature, for example. So that would be good something to keep abreast of. Some other areas are new polymer systems, so fibers that swell when they're wet. So these are sometimes bicomponent fibers that will swell up when the surface will swell when it gets wet, and so close up the pores in a fabric structure, and then once it becomes dry, it would open up again. And so this would be an area of interest for analysis, because it would potentially impact your FTIR analytical techniques, for example. Another possibility is waterproof techniques where you don't have any surface chemistry is applied because of the selection of the bicomponents. Okay, so what can we analyze? I'm going to pass through a few things because I think one of the things I've learned from this symposium so far, there's lots of fantastic experts in analytical chemistry, and I'm not really going to get into that too much, so I'm going to pass over this slide, except to say we've got microscopic level, microanalytical, and then chemical analysis. And so at the macroscopic level, we can look at weave structures, fabric densities. I'm going to pass over this. As I said, there's a lot of growth in microfibers. And so we're seeing, these are some examples of images of microfibers. This is a standard type of cross-section here compared to the microfiber. And the shape of the fiber is often indicative of the manufacturing process. Synthetic fibers, as I'm sure you're aware, can have many different cross-sections, and those shapes are growing. There is more development here, for example, in hollow fibers. And then in chemical analysis, one thing to consider, and I haven't really looked at this in detail, but cotton, for example, is often, of course, very difficult to analyze and separate one batch of cotton to another. But one issue to consider is the level of metals in a particular cotton fiber. If cotton fields are irrigated during a drought, for example, in Texas, they're likely to have an order of magnitude more metals such as iron and magnesium than if they were not irrigated significantly. And so that's an area of differentiation potentially. Chemicals that are applied to textiles that might be analyzed during, that could be applied during manufacture or consumer use include, and so one of the areas of research in my view is how do you get a non-destructive test for these kind of chemicals that will likely be present on a lot of fibers. Softeners, flame retardants, water repellent finishes, stain repellent, crease resistant, antimicrobial finishes, fluorescent brining agents that are present in some polyesters during manufacture, UV blocking finishes. And then in the consumer use, laundry detergent formulations are extremely complex and they have specific chemicals that are added. Fragrances is one, which I haven't listed here, surfactants, brining agents, softeners, antistatic agents is another possibility that we might be able to analyze. So let me just tell you just a couple of minutes on some aspects of nonwovens. That is a very fast-growing area. It's extremely low-cost production, and in the United States has the lead in this area, and the West, and Germany also. So it's a $50 billion market. They're mostly in things like disposables, materials, medical applications, also filtration, protective garments, interlining, shoe linings, things like that. So they are in a lot of different application areas. And this just shows you a picture of some of the nonwovens. So it's more non-traditional fibers. So nonwovens is exactly what it indicates, that the fibers are entangled in some way that isn't weaving or knitting. And I don't think I'll have enough time to really talk about the manufacture of these fibers, but suffice it to say that basically fibers are loose fibers are oriented in some way. This is what is called a carding machine where the fibers are entangled. We can do it wet or dry, and it forms what we call a web. And the web can also be made from a polymer. So the polymer goes into an extruder that then extrudes strands of fibers that are short fiber lengths, and then they are entangled on a web in some cases. The web has to be bonded in some way. We have to find some way to give it durability. This can be chemical adhesion. It can be mechanical needle punching to force the fibers into an entanglement. It can be hydroentangling through water addition or thermal bonding. So all of these will produce specific characteristics that are analyzable. Very fast process, as I indicated. So let me tell you a couple of things of biocomponent fibers that looks interesting, and then I'll wrap it up. Biocomponent fibers are relatively new in terms of their production in a very consistent way. But they are very interesting, and this slide basically indicates that we could have two different polymer systems, let's say A and B, and they are mixed in they're melted and mixed in an extruder head, and the way that they are mixed is absolutely critical. So there's a lot of engineering in this process, and we can form all sorts of different patterns. And so the bicomponent fibers that variants that we see are, this is called a sheath core. We can have different ratios of one polymer to another in a particular fiber. And in fact, let me pass over this and I'll show you a few images. So here is an SEM image of a sheath core type of polymer structure that could be analyzed by IR. The imaging poster that I saw, imaging IR, would work very nicely with this, and I think I saw some images of it in the poster. Here's another picture. Here are some other unusual type of bicomponents where we have a trilobal structure where one of the lobes is one particular material. So we can really engineer very significant chemical and mechanical properties. Here, each one of the lobes has a different fiber structure. These are called pi segments, and each one of these images segments is a different polymer. Sometimes we can dissolve out one of those polymers in a solvent and to leave very fine fibers. And here you can see some more as well. Concentric rings. This is 37 islands in a sea, what we call. So these have 37 different fibers in a fiber structure that then the sea is actually dissolved away. And again, you can see some images here. Some hollow fibers, so very highly insulating materials. And this is really pushing the envelope as the maximum number of nanofibers that we've been able to generate today. I say we at the Nonwovens Institute at the College of Textiles is 600 islands in the sea. Tri-segments, so 3 component fibers as well are coming. And so this is an area that's intended to grow, is seeing about 10% yearly growth, and approximately 75% of all bi-component fibers are going into the nonwoven sector right now. So here are some of the applications, just briefly. Medical applications, plasters, stitching, that kind of thing. Garments for surgeons, filters. And Thinsulate is one of the commercial products that is used for commercial applications. And here you can see an image of large and very fine nanoparticles that are intermixed to improve the filtration process. So I think I'm out of time. I've got a wrap it up sign right here. So I'm going to stop here, and hopefully I can answer any questions you have if we have time at the end. Thanks very much.